Starting Chapter 7 in our statics textbook, and the title of Chapter 7 is Internal Forces and Moments. So the material in this chapter builds directly on the material in Chapter 6, where we're looking at the internal response of a structural member to an external load. Now, if we take a look at our web page, we can see that we will have 3 lectures, 27, 28, and 29, and that we will cover sections 7.1, 7.2, and 7.3. So today we're just going to cover 7.1, and I've already written 2 problems for homework assignment, 7.1 and 7.3. Then at the end of today's lecture, I'm going to do section 7. Not section, but I'm going to do problem number 7.2. So the main thing that I would like to emphasize in Chapter 7 is that we are building directly on Chapter 6. And in Chapter 6, we talked about the fact that if you have a 2-force member, in other words, if you have a truss, and it is either going to be acted on in tension or compression, that you can look at each member individually and decide what forces are acting on it based on this internal response. So what we're doing in this chapter is we're doing the same thing, except for now, instead of having 2 force members, we could have a structural member that has both normal forces, tension or compression, but could also have a shearing force, which is perpendicular to the normal force. So in other words, if we have a structural member like here, structural member BE, we could have a force acting along BE, and we could also have a force acting perpendicular to BE. So the forces acting along the structural member are called normal forces, and that would be either tension or compression. The forces perpendicular would be called shearing forces. Now, shearing forces, the sign of a shearing force, whether it's positive or negative, is less physically meaningful than for the normal forces. So we will discuss it in terms of a sign convention, but finding it is not just knowing the direction so that you know if it adds or subtracts from other shearing forces is what's important. So a sample problem here, we have this frame, and we want to determine the internal forces in member ACF. So the difference here is that we have a pin at C, which means that there will be forces acting at C as well. But so the basic way that we solve it then is to compute the reaction. So once again, we take a look at this frame as an entire structure, and we know that we have a 2400 Newton force acting down here at point D, so we compute the reaction forces at E and F. And then to find out what's going on at J, we cut the member ACF at J. So after we determine those external forces, we look at either the portion from A to J and what's acting on that, or the portion from J to F and what's acting on that, because we're interested in what's going on here at J. Now at J then, we could have a normal force, which could be either tension or compression. We could have a shearing force, which, as I said, has a sign, but the sign doesn't have as much physical meaning as tension and compression. And we can also have a moment acting at J. And so we're going to do that external statics first. 2400 reaction forces F. We're going to sum moments about E. And that gives us the reaction force here at F. And then we do summation of forces in the Y direction and summation forces in the X direction to find E sub X and E sub Y. All right, now after we do that, we're going to look at this internally. And so the first thing that we recognize is that to find what's going on at J, we're going to have to find out what's going on at C. So we take this piece, BCD, which as you recall here, BCD right here, and we're doing that so that we can find the reaction here at C, so that we can then use that force at C to find the forces at J. All right? So we find this. We find the forces. I think I went down one too many. Here we go. So we go on this cross member, BCD, do our statics, moments, forces, and then we also are going to take a look at ABE, because we need to get some reactions here at A. And then we have F, we have C, which we just found from above, and then we have A. So then, since we're cutting J, we want to look at J, which is right here. We then have the structural member that's going to allow us to do that. All right, so after we get all of those reaction forces, we consider point J, and you see we split this structural member right at point J. Now the directions for those forces, like we said, are the normal forces, which they call force F, the shearing force, which they call force V, and the moment at point J. So then, considering either A to J or F to J to be the piece that we're looking at, we do a summation of moments, summation of forces F, X, and summation forces Y. Now, it's important to notice here that X and Y, we have reoriented our axes so that X is along the structural member and Y is perpendicular to the structural member. And we do that because F then, which is in this new X or X prime direction, is going to be our normal force, and V, which is in the Y prime direction, is going to be our shearing force. All right, so then this is when we're looking at point K. So this is really the only piece that I wanted to look at. All right, so we're really building on those techniques that we developed in Chapter 6 in order to finish working with this idea of the internal responses. All right, so having said that, I'm going to take a look. I'm going to assign to you 7.1 and 7.3. And what I want to do in class is to do problem 7.2, which refers back to problem 678. So I'm just going to grab my book here, and you know, I don't really like this problem as much as I had intended to. That's all right. 678. Let's just take a look at 678. All right. So we are, oops, you probably want to see that picture. And we are looking at this piece right here, which says determine the components of all forces acting on member A, B, C, D as shown. And then problem 7.2 asks us to determine the internal forces at point J, which is right here. All right? So what I really want to do is, even though problem 6.78 calls for us to analyze this piece, what I really want to do is to analyze this piece, because that's where point J is. All right? So I'm going to draw the whole thing, and then we're going to do our analysis. All right. So this is problem 7.2, not 6.2, which refers to problem 6.78. All right. So the first thing I'm going to do is to draw this entire frame, or at least assembly. I don't know if I can really call it a frame, maybe. So what we have is this piece that's sitting on a roller that is pinned here at B. Okay. And it comes through this like this. Okay. So we have a ball here, and we have a ball here. then this is jointed here at point A. This is point B. This is point A. And we have a second piece that looks like this, that is sitting on top of this ball at C, and that we have a 120-pound force acting here at point E. This is point A. And we are interested in what's going on here at point J. All right? Just to make sure I have everything labeled. This is D. So we have A, B, C, D, E, and then we have point J. All right. So the first thing we need to do is to find out our reactions. We have something going on here at C. We have something going on here at D, and something going on here at B. So the first thing that I want to do is to take a look at the entire structure. And I want to find my reactions. Now, a couple of things to keep in mind. The only thing that these balls can do is to push perpendicularly to themselves. But B, because it's a rigid connector, can act like this. We can have a reaction at B in the X direction and a reaction at B in the Y direction. But here at C, we just have this internal load, which is going to be equal and opposite. And here at D, we're going to have a load pushing up. All right. So in terms of my analysis, I can say that the summation of forces in the X direction on the overall structure have to equal 0. The summation of forces in the Y direction also have to equal 0. And the summation of moments about any point on that object also have to equal 0. All right. So if I consider, I have two different ways that I can do this. I can consider the reactions at C to be part of the structure or not part of the structure. But the one thing that I can see is that because the ball C is not getting squished and is not moving, that you're going to have an upward force acting on the top part of the member and a downward force acting on the bottom part of this member, and that the two are going to have to be equal and opposite, aren't they? So in other words, if I look at the entire structure, I can eliminate this from my discussion. It's going to come into play later on, but right now I can eliminate that. So in terms of summation forces X, I have this 120-pound force acting at E, and the only thing that's going to oppose that is my reaction in the X direction at point B. Those two things have to sum to 0, which means that my reaction at point B in the X direction is negative 120 pounds. So this is what my reaction at B in the X direction looks like.
Oh, because it was leftwards.
Exactly. That's exactly right. Now, in the Y direction, if I consider these to be equal and opposite, or consider them to be internal, I'm going to have the reaction at C in the Y direction and the reaction at B in the Y direction. And those are the only two Y-directional forces acting on this structural member. And this should be, I apologize, this should be D right here. C is the ball internally. And those equal 0. So I can't really break that out, can I? So the way that I have to do that is to sum moments about a point to determine what that's going to be. So I'm going to sum my moments about point B. I could have chosen point D as well, but I'm just choosing point B. And that will eliminate the reaction at B in the X direction and the reaction at B in the Y direction from the moment equation. So what that means is if I put a pin here at B and I look at that force, the Y-directional force at D, and I think about what kind of a spin it's going to be, it's going to be counterclockwise, which is positive. So I can say the reaction at D in the Y direction, since it's vertical, times this horizontal distance between B and D, and my diagram shows that to be 4 inches plus 2 inches. or 6 inches. And then the only other force is going to be this 120, which is going to be making it go clockwise, which is negative. And since it's a horizontal force, I need the vertical distance, which is 4 inches. And those are the only two external forces acting. So I can solve them equal to 0, which means I can solve for r dy directly, equals 120 pounds times 4 inches divided by this, which is 6 inches. Inches cancel out. And I get that my r dy is, well, if I take 120 and divide it by 6, that's 20, isn't it? 20 times 4 is 80 pounds. So my reaction at D in the y direction is equal to 80 pounds, which means that my reaction at B in the y direction, this is a positive 80 pounds. Those two things have to equal 0, so r sub by is equal to negative 80 pounds. All right, so that means that RBY looks like this. All right. So now, since I'm looking for this going on at point J, I'm also going to have to find this force. I need to look at this structural member, just this piece of it. That looks like this. And I have a reaction at A in the y direction, a reaction at A in the x direction. I also have a reaction at C in the y direction. But as I can tell, this is a ball. It's not going to support an x directional force, just a y directional force. And then here at point E, I have a 120-pound force. Okay, so on this structure, remember once again, I can say summation forces x equals 0, summation forces y equals 0, summation of moments about any given point will also be equal to 0. And so if I take a look at this, I'm really going to want to get rid of this, the moments from RAX and RAY. So I'm going to sum moments about point A. And that's going to simplify it. I pretend like I put a pin here. RCY, which is a vertical force. C is 4 plus 4, or 8 inches from point A, since I'm taking the moments about A. And if I put a pin here, that would spin it counterclockwise, which is positive. Then the only other force I would have would be this 120, which once again, if I put a pin here, that's going to spin it clockwise, which is negative. Horizontal force, so I need to use the vertical distance. From E to A, my diagram tells me, is 2 inches. And those two things sum together equal 0. So that means that my reaction at C in the y direction is equal to 120 pounds times 2 inches divided by 8 inches. So this cancels against this. This is a 4 then. So I have 120 divided by 4, which is 30 pounds. That means that the value of this is 30 pounds. All right. Now I can do my reactions at A by its summation of forces x. Reaction at A in the x direction plus 120 pounds here, that's my only other x directional force, is equal to 0. RAX then is equal to negative 120 pounds to maintain static equilibrium. So it goes that way. That's 120 pounds. RAY, if I look at this, I have 30 pounds going up, plus RAY equals 0. So RAY equals negative 30 pounds. So this looks like this. Okay. All right.
Well, it's logical since we have the counterclockwise.
Perfect.
So that
Yes.
If we do the scale, we have to go this way then.
Perfect.
So that's why.
Absolutely perfect. Absolutely perfect.
How do you put a pin in to determine whether it's counterclockwise? You just
Right.
put a pin in
I do it just in my mind. I mean, it sounds like a silly thing, but I just pretend like it's anchored right here. And then I look at this force and I say, if I were to pull on this force, like this is anchored, so I just got this little thing, it rotates clockwise or counterclockwise.
Another force makes sense here. Another action makes sense here. RCOY.
Yes, yeah, exactly. So it's just my little mind movie to make it go.
Okay.
All right. So now we're on to the final step. We want to know what's going on here at J. And at J, we can have a normal force, which is directed along the structural member. We can have V, which is perpendicular to the structural member. And we can have a moment at point J. All right. And the way that we do that is we either look at the piece of this structural member from A to J, or the piece of the structural moment from J to the end. And it absolutely does not matter which way we do it. But we cut it at J, and then we look at one or the other. Okay? So what I'm going to do for that, here's my cut at point J. I'm just going to cut it this way. Like I said, it really is going to come out to be exactly the same. But I'm just going to look at this. Okay? And then we have RCY, which is 30 pounds. And we have this applied force, 120 pounds. And then here at point J, we draw three different things. We draw F, directed along the structural member. We draw V, directed perpendicularly to the structural member. And we draw a moment at point J, just as a little thing. So this kind of a drawing is sort of key to this analysis. So we just say when we cut it, we have three things going on at J. We have a force F that runs along the same direction as the structural member, a force V, which runs perpendicularly to the structural member, and a moment. All right, so now I take about point J on this chunk, summation forces X equals 0, summation forces Y, equals 0, and the summation of moments about point J also equals 0. So what do we have in the X direction? Well, we have a negative F, right? And we have a positive 120 equals 0. So that tells me that 120 is equal to F. 120 pounds is equal to F. Okay, we know this is positive. We know that that means the structural member is in tension. And it is, because we're pulling on it. So it's positive, and we just write that as being tension. Now, in the Y direction, we're going to have these V forces. So here we have negative V. So we've drawn it downward. We have positive RCY, which is 30 pounds equals 0. So that tells me that 30 pounds is equal to V. Now, like I said, we don't know, there's not like a tension compression meaning for that. All it means is because this sign came out, it didn't have a negative in it, that I drew it correctly over here. Okay? Okay, now what about the moments? Well, let's think about right here, putting a pin in J, and we have this moment at J, right? We don't know what it is. That's what we're solving for. But from here to here, we have a moment from RCY, and if I think about that push pin thing at J, yeah, we can see that that is going to be counterclockwise, which is positive. So that's 30 pounds. It's a vertical force, so I need the perpendicular distance from J to C, which is 4 inches. And then here, if we put that pin, we've got a clockwise spin, which is negative 120, times this distance. Now, this is a horizontal force, so we need the vertical force, which is 2 inches, equals 0. And what do we find about the moment at J? The moment at J plus 120 minus 240 equals 0. So that means that it's equal to 240 minus 120, or 120 inch pounds. Okay? So 120 inch pounds is equal to the moment at point J.
That's the final answer.
And that is the final answer. These three numbers are the final answers. Yep. And so, so yeah. So that will get us through that problem. Do you need it? Do you have any questions about that? Not right now. Good answer.
All right. All right. No.
Perhaps later. Perhaps later. Well, you know where I'll be. Do you have? I'll go ahead and post this page just with this work on our Moodle page so that you will have it. And then, if you have any questions, just make sure that you get hold of me, and I'll answer that for you. Now, the other thing is, like I said, on the homework, this is problem 7.2. You'll do problem 7.1 and 7.3, and they will be very similar. Yeah, it's the same solution method, and it is very rigorous, I would say, in that you sort of have to go through all the steps, and I think that you're really good at that, but it's just, at first especially, it's not a great idea to look for shortcuts. Not that I think you would, but if you just take it like one step at a time, that's why I've only given you guys 2 problems, because I want you to have enough time to just really work these all the way through. And they are time consuming.
Sure.
All right? All right, thank you for your time, and we'll look forward to seeing you Wednesday.